Alright, so in this video we're going to be going over basic titration curves. So when we are titrating something, basically we're trying to figure out the unknown concentration of some solution. So it is a technique where we use a burette, which has a liquid where we do know the concentration of that liquid, and we pour it into our unknown concentration until we get a color change. So usually there's an indicator in the solution and it will change colors when you hit the equivalence point, or really the end point. Okay, so you need to know some vocabulary terms. So the solution in the burette is called the titrant, and usually we do know the concentration of this. And that's added to a solution with an unknown concentration. That's the titrate. So that's going to be in the flask or the beaker, whatever you're pouring the solution into, the titrant. And you do that until the moles of the titrant are equal to the moles of the titrate. So if you know the concentration of this and you keep adding a certain volume, when you get to that certain volume, you're going to know how many moles you added of that. And then that's how you're going to be able to figure out how many moles per liter you have in your titrate. So the equivalence point is when the moles are equal to each other. And usually that's seen with a color change, which is what the indicator's job. So that's called the end point. But usually the end point is actually a little bit after the equivalence point. So there will be a color change, but usually after you have hit your equivalence point. So when we look at acids and bases, we use titrations a lot. So when we titrate acids and bases, there's going to be a change in pH. So a titration curve can actually show this pH as your titrant is added. And at the equivalence point, there's a rapid change in pH. So basically, as you add a little bit of your acid or your base, there's only a slight change in pH until at the equivalence point or the end point, when you have moles of titrant, and that's equal to the moles of the titrate. All right, so this is what it looks when you have a strong acid and it's titrated with a strong base. Your pH will start off very low, okay, and your pH will end up high. It'll end up towards 14 and start off very low, and your equivalence point is going to be at 7. So your equivalence point can be found when you have a steep, dramatic change in pH. So right at that middle point, that is your equivalence point. So my pH here will be 7. Now keep in mind, if you had a strong base and you were titrating it with a strong acid, this would actually be the opposite. Your pH would start off very high and your pH would end up very low. So you need to keep that in mind. Whenever you're asked, okay, what should the titration curve look like? If you're titrating a strong acid, you're starting off with a pH that's very low. If you're titrating a strong base, your pH should end up very high. So it really depends on what the question is asking. You need to be careful about that. All right, so if I titrate a strong acid with a weak base, if I titrate that strong acid, I'm going to start off with a low pH, and then I'm going to end up with a pH above 7, but not as high. So with a strong base, I should end up closer towards 14, but if it's a weak base that I'm adding, it's only going to be, it'll be above 7, but not quite as high as a strong base would end up. So if I'm looking at this, I'm going to start off low. My equivalence point will be the middle point right here, and then that's going to be below 7. So basically, if you're trying to figure out where the equivalence point should be, the stronger of the two will essentially win. So if you have a strong acid, your pH should be below 7. If you have a strong base, your pH will end up above 7, or your equivalence point. All right, so let's look at what it would be, or what it would look like if I had a weak acid and I titrate that with a strong base. So my pH will still end up low, but it's not going to be as low. and it's going to end up high, so closer towards 14, and my equivalence point will be above 7. So we have a strong base here, so my equivalence point will be basic. It'll be above 7. All right, so when I have a weak with weak, well, it's not going to be a very dramatic curve. I'm still going to start off low, but not as low as a strong acid, and I'm going to end up above 7, but it's just not going to be as high as it could be with a strong base. Now the equivalence point will usually be somewhere around 7, but it can be below 7, it can be above 7. It really depends on what your conjugate acid or your conjugate base is. So, and that's something we're going to talk about later. But this will vary. Like the equivalence point of a weak with weak will vary, and it really just depends on what you make as your conjugates here. All right, so when you're setting up your titration, you want to pick an indicator that's going to be appropriate. And the way that you're going to know that it's appropriate is because the indicator, well, the pH range of its color will change at a certain point. So methyl orange will change between 5 and 6, and it turns from red to yellow when it becomes basic. Methyl red will change between 6 and 7, and it goes from red to yellow if it becomes basic. Well, you're going to pick your indicator with a pH range that's close to where your equivalence point will be, because that is going to signal, hey, stop adding your base or your acid. Okay, so phenylalethane is colorless and it will turn pink, and it has a pH range of 9 to 10. Now litmus paper, it's just an indicator you do need to know. If you have litmus paper and it turns red, that indicates there's an acid there, and if it's blue, it indicates there's a base. All right, so you're going to choose your indicator based on your equivalence point. So you want to pick the pH range with, pick an indicator with a pH range that is close to your equivalence point. So strong with strong, almost any indicator will really work. A weak acid with a strong base, phenylalethane is the best. Strong acid with a weak base, methyl orange would be the best. And for weak acids, weak bases, because the pH change is not going to be as dramatic, you really need to have a pH meter instead of an indicator. This is the other type of titration curve you will see, and this is with a polyprotic acid. So a polyprotic acid is one that has more than one hydrogen that you could pull off. So sulfuric acid would be one. Looks like this. Or phosphoric acid. Basically, if you have more than one hydrogen that can be donated, it's polyprotic, but only one hydrogen is removed at a time. So when I look at this, I have multiple equivalence points, and that's because you're pulling off one hydrogen at a time. So in this titration curve right here, this is similar to what you'd see for sulfuric acid. You're going to pull off the first hydrogen, and then if you keep adding a base, well, eventually the second hydrogen will come off as well. And then you're going to see another equivalence point. So you actually have a Ka for every hydrogen that you pull off for polyprotics. That's why you'll see with sulfuric acid, you have a Ka1 and also a Ka2, because you can pull off two hydrogens, but only one of them comes off at a time. So this is what you're going to see if you have a polyprotic acid.